This is Mr. Boudreau again. Here are a few comments on probability distributions. The binomial distribution is a discrete distribution, meaning its outcomes can be counted. Things like the number of defects in a bin, or the number of Republicans in a political action committee. In order to recognize a binomial distribution, there are four main requirements. These are outlined in your text. First, only two outcomes are possible. So it's heads or tails, or either or true or false. Second, the probability of each outcome is known and is constant. Third, the number of trials is known and constant. And four, the successive events or trials are independent. The result of one trial has no impact on the result of the following trial. Let's look at an example. Here, 33% of the population has a particular gene sequence. If 9 patients are tested, what is the probability that 4 of these patients have this gene sequence? Now, is this a binomial experiment? We need to check it against the 4 requirements. First, are there 2 possible outcomes? Yes, patients either have or don't have the gene sequence in question. Second, there is a constant 33% probability of any patient having this gene sequence. Third, there are 9 trials or patients specified in this problem, a concrete number of trials. And fourth, one patient's having or not having the gene sequence has no impact on the following patient having or not having that same gene sequence. Therefore, trials are statistically independent. We meet those 4 requirements, therefore this is a binomial experiment. Now, let's look at solving this problem and finding the probability of exactly 4 patients out of the 9 having this gene sequence. Here's an illustration of the outcomes of this problem. There are 10 possible outcomes out of 9 trials. Either 0 patients out of 9 can have this gene sequence, or 1, 2, 3, 4, up to all 9 patients having this gene sequence. I've also given the probabilities here. We can calculate them individually, and we'll start with looking at one probability in particular. That's the probability of exactly 4 patients out of 9 having this gene sequence. Here's also an illustration of the probability distribution for this specific binomial trial. There are 9 patients or trials, so n is equal to 9. We have a probability of 33% of any patient having this gene sequence. Out of 9 patients, if each patient has a 33% chance of having this gene sequence, 33% of 9 is equal to 3. So the most likely outcome out of 9 trials is to see 3 patients having this gene sequence. Seeing 2 or 4 patients is also fairly common. Finding fewer patients or more patients with this gene sequence is a much more rare event. Here's how we can calculate the probability of exactly 4 patients out of 9 having this gene sequence. This is the formula that's outlined in Activity 7.3 in your textbook. It's a rather complex formula. All the values are given. N is equal to 9 trials. R is equal to the 4 that we're interested in, 4 patients out of 9. Our probability of a patient having this gene sequence is 0.33. And those 3 values are all that you need to calculate this probability. Now, this is a rather difficult and cumbersome calculation here. We can use the power of Excel, however, to calculate this for us. All we need to do is tell Excel that we have a binomial distribution and we need these 3 input parameters to define the distribution. Here's how it's done in Excel. We identify that we need a binomial distribution calculation. R is equal to 4, N is equal to 9, P is equal to 0.33, and we have this cumulative parameter, which in this case is false. if we enter those 4 parameters into the binomial distribution, you can see that it calculates exactly the same probability as the mathematical formula. Now let's look at this cumulative probability function here. First, on the left, we're asked what's the probability of exactly 4 patients out of 9 having the gene sequence. We already calculated that as 0.2017. Here's an illustration that shows we're calculating the probability of only one outcome, the probability of x exactly equaling 4. So we're not accumulating or summing the probabilities of several outcomes, we're only looking at one. It's not a cumulative calculation, so our cumulative parameter in this case is false. However, if we want to calculate the probability of 4 or fewer patients having the gene, you can see that it's equal to the sum of the probability of 0 patient, 1 patient, 2 patients, up to 4 patients having this gene sequence. Now we are accumulating probabilities, so the cumulative function is true. Excel always calculates the probability of being less than or equal to any value specified. So when we enter in the binom.dist formula a value of r equal to 4 and we have the cumulative function equal to true, then Excel is calculating the probability of x being less than or equal to 4. Let's look at some other applications of this binomial distribution. Next, what's the probability of strictly less than 4 patients having the gene? Previously we asked for less than or equal to 4. Now we're asking for the probability of less than 4 patients. It's a good idea to write out on a piece of scratch paper each possible outcome of the experiment. In this case, our outcomes are 0, 1, 2, 3, 4, up to 9. The question is, what's the probability of less than 4? So circle the outcomes, identify those outcomes out of the 10 possible that are less than 4. It's x equals 0, 1, 2, or 3. So with the knowledge that Excel only calculates less than or equal to probabilities, then the probability of x being less than 4 is equal to the probability of x being less than or equal to 3. Okay, and the fourth potential question we can ask is, what's the probability of more than 4 patients having the gene? Remember, Excel can only calculate less than or equal to probabilities. But here in our illustration, we want to know the probability of 5, 6, 7, 8, and 9 possible patients. Since all probabilities must sum to 100% or 1.0, then the probability of having more than 4 patients is 1 minus the probability of having less than or equal to 4 patients. So we subtract the binomial distribution cumulative function from 1, and in this case we get 0.1398. That's binomial distributions. I hope you find the solution to binomial problems straightforward using Excel.